At this point, we're getting into the trigonometric component of our Algebra 2 class. And so questions number 43 and beyond in our review ask you to solve for different components of a right triangle. And if you recall, when working with a right triangle, the phrase that you need to remember is SOHCAHTOA. And this phrase reminds us of which parts of a triangle must be present in order to use specific trigonometric functions. So the S letter stands for the phrase sine, C stands for cosine, and T stands for tangent. And so sine, cosine, and tangent are the name of the functions that we use on our calculator. So if you reach for your TI calculator, you can see sine, cosine, and tangent listed initially here. And if you're using a more basic calculator, then it's quite possible that you have a series of buttons dedicated to those commands. Now, with regards to the sine function, O and H stand for opposite and hypotenuse. So the opposite side length and the hypotenuse of the triangle must be present in order for us to use the sine function. For cosine, we need an adjacent side length and the hypotenuse of the right triangle. And then finally, with tangent, we need the opposite side length and the adjacent side length provided. When we talk about these side lengths as they're being provided, it's all relative to the position of the angle in question. So in example number 44, we have an angle that's unknown that we're looking for down here in the bottom left-hand corner. And as we're trying to decide what other information is given, we might look directly across from that angle measure and notice that this side length 7 is given. This is what I would consider an opposite side length because it is across from or opposite to the angle measure in question. Right next to the angle measure, we've got a side length of 12, and I would call this the adjacent side length because the adjacent side length is right next to the angle measure. And you might be asking, well, what if there was a side length up here? Wouldn't that also be next to the angle measure? And that's true. However, this side length happens to be the longest side length of a triangle, and its measurement would be considered on the hypotenuse of the triangle. In this particular case, we have an opposite side length and an adjacent side length, so I know that I'm going to have to use the tangent function to find the angle theta. So as I set up the equation, it's going to look something like this. Tangent of theta, we always use the angle measure next to the trig function, must be equal to the opposite side length 7 divided by the adjacent side length 12. And you'll recall that theta is the variable in this case. We sometimes write this series of functions with the letter x here. We can still solve for x. But unlike traditional algebra problems, it's not like we can divide tangent from both sides of the equation. That's not really an appropriate method to eliminate tangent in order to isolate our variable. Instead, what we have to use is the opposite or inverse of tangent in order to isolate this theta or this variable. So if I apply the tangent inverse command, truthfully, it would look something like this. Tangent inverse surrounding this command, and then again, tangent inverse surrounding this fraction. Let me see if I can just rewrite that over here. So we've got tangent inverse of 7 over 12. Then what's going to happen is this tangent inverse and this tangent is going to cancel, and we will be left with theta, what we're looking for. And all we need to do is execute this result, tangent inverse of 7 divided by 12. Unfortunately for us, our calculators are built to handle that very nicely. So if I press the trig button and then ask for the tangent inverse command, I can write 7 divided by 12 and press enter, and we see our result as 30.2564. So this angle measure is apparently 30.2564 degrees. Now, if you are using one of my TI Nspire calculators in the classroom, double check to make sure that it says degree in the top right-hand corner. If it says RAD for radian, then you're going to get results that are not correct. Let's try another example. In 46, we have an angle measure that's here in the bottom right-hand corner, and immediately next to or adjacent to this angle measure is side length 5. So again, I'm going to call this the adjacent side length. And 14 may be a bit deceiving at first, but you should notice that this is also, or this is the longest side of the triangle. So this one I'm going to call the hypotenuse. You'll also notice that this side length is always going to be across from the 90-degree angle. So if we're dealing with an adjacent side length and a hypotenuse, we must be dealing with a cosine function. So cosine of theta is equal to 5 over 14, adjacent over hypotenuse. Therefore, theta by itself must be cosine inverse of 5 over 14. And if I reach for the calculator to solve this, we'll see that cosine inverse of 5 over 14 is 69.0752 degrees. For the next group of trigonometric questions, we have to get a bit creative here. These are all right triangles, but the instructions simply say to solve each triangle. So remember, what that means is to find all side lengths and angle measure, all sides and angles. So not just one side or one angle, but we need to find all of them. And so you should recall that capital letters are being used to identify angle measures. So capital A we don't know. Capital B we do know is 65 degrees. And capital C we also know that's 90 degrees. Lowercase a, b, and c represent side lengths. Now, the side length across from angle C, we call that side length C. So I know that side length C is 3 kilometers in this case. But I don't know what side length A or B is. Now, you should also recognize or recall that the sum of all three angle measures must equal 180 degrees. And so if we know what two of the angle measures are, it's not too hard to find the third. We could take the 180 degrees minus 90 for the right angle, and in this case, minus 65 for the obtuse angle. We recognize that this missing angle measure here is 25 degrees. We could even mark that on the diagram if we wanted to. And with that angle measure known, that gives us some options when looking for side lengths A and B. Now, if I'm going to start with angle B, and let's say I'm looking for side length B, which is this side over here, what I might recognize is that this is an opposite side length, and we're also provided a hypotenuse side length in the triangle already. So the sine function, sine of 65 degrees, should equal the opposite over the hypotenuse. So let's jump over here. This is problem number 48. So I know that sine of 65 degrees will equal the opposite side length for side length B, and that should be divided by our hypotenuse, which is 3. Since my job is to isolate B, to get B by itself, we would multiply both sides of the equation by 3. And as it turns out, this value for B can easily be identified. All we need to do is ask the calculator to tell us what 3 times sine of 65 degrees is. So 3 times sine of 65 degrees is 2.7189. So we'll say that side length B is 2.7189 kilometers. And here again we have options for finding side length A. We know 2 of the 3 side lengths of this right triangle, so we could use the Pythagorean equation. But for me, I'm going to note that side length A is the opposite of angle measure A. And again, we were provided the hypotenuse before. So if I'm looking for side length A, I might say that sine of 65 degrees is equal to A divided by 3. A is the opposite side length of 65 degrees. So therefore, A by itself, much like we saw with B, A is going to be equal to 3 times sine of 65 degrees. So 3 times, whoops, let's try that again. 3 times sine 3 times sine of 65 degrees, whoops, wrong button there, is 2.7189. And boy, I must have been distracted there. Hopefully you caught my mistake. Um, Angle measure A is not 65 degrees. Angle measure A is 25 degrees. So it should be no surprise that we actually got the same answer there. My mistake. Let's try that again with 25 degrees. So we'll say 3 times sine of 25 degrees. There we go. 1.2679. 1.2679 kilometers. 1.2679 kilometers. And now we've solved the triangle. We have all angle measures and side lengths to that triangle, and we are finished. So I'm going to complete the last example silently here. I think I was a little bit distracted with what was going on around me. So take note to how I'm completing this next problem using very much the same techniques as before, and I believe you should be able to use this as reference to complete your problems on your own. Thanks for watching.